Okay, so we're going to go over section 4.2. The good news for you guys is I went over a lot of what was or what is in this section in the previous section in 4-1. So there's not going to be as much for me to go through in this lesson 4.2. So you guys are going to love this section, especially in comparison to what you guys did in section 4.1, because we can start taking the derivatives of functions much more easily and much more quickly now. Okay, so we're going to take a look at basic differentiation rules, namely the power rule and rates of change. We've already talked about rates of change, both average rate of change and instantaneous rate of change in the previous lesson. Okay, so let's take a look at the power rule. So it says the power rule can only be used for polynomials or functions in polynomial forms. Okay, so you guys know what a polynomial function is. When we say functions in polynomial forms, that means that we can write the terms as like f of x equal to x raised to some numeric power. So like x to the 2/3 power, that's not a polynomial function because the exponent is a fraction, but this is in a polynomial form because we can write that as x to the 2/3 power. If we had the function like f of x equal to 1 over x, that's also not a polynomial function. It's a rational function, but we can write that function in a polynomial form. I can write that as x to the -1 power. And as long as you can write your function in a polynomial form, you can use power rule to differentiate it. Okay, so what power rule says is if we let f of x equal x raised to the n power, where n is a real number and n cannot be equal to 0, then if we want to take the derivative of that function, what we do is we pull the exponent out front. So we get n times x, and then we drop the exponent by 1. So it's going to be n times x raised to the n-1 power. Okay, so that's how we take the derivative of a polynomial function or a function in a polynomial form. So let's do just a really quick example with this to get the hang of it. Okay, so let's say we have the function f of x equal to x to the 4th power minus x plus 2. So that is a polynomial function, so I can use power rule to differentiate it. So the derivative of that, the derivative of x to the 4th would be I pull the exponent out front, that's 4 times x, raised to the, and then we're going to drop the exponent by 1. So it goes from 4 to 3. So that becomes 4x cubed minus x is like x to the 1st power. So we can write that as like 1 times x to the 0 power. And we know x to the 0 power is just 1. So that's 1 times 1, which is 1. And when we take the derivative of a constant term, like if you picture the constant y is equal to 2, the slope of that graph is 0. So again, derivative measures slope of our graph. So the derivative of any constant is going to wind up becoming 0. So the derivative of 2 just becomes 0. Okay, so our derivative here, f prime of x, is going to be 4x cubed minus 1. Way faster, way easier than using the difference quotient, okay, for this. Okay, so again, you guys only have to use the difference quotient in the homework for 4.1. Okay, again, you have to use it in the homework for 4.1. If the problem does not specify, I want you guys taking derivatives like this moving forward. Okay, if you can use power rule from section 4.2 and beyond, I want you to use it. Okay, so let's do some more examples with this. So directions for these examples ask us to find f prime for number 1. We're given f of x equal to x cubed plus 4x squared. So if we want to take the derivative, this function here is a polynomial function, so we can go ahead and take the derivative term by term. The derivative of x cubed is going to be 3 times x, and then we're going to drop the degree of the exponent by 1, so that's 3x squared. And then to take the derivative of the next term, 4x squared, I'm going to pull the coefficient out front. So I'm going to pull 4 out front, and then take the derivative of x squared. So the derivative of x squared using power rule is going to be 2 times x raised to the first power, which is 2x. So that's going to make f prime equal 3x squared plus 4 times 2, which is 8x. If you want to jump from like eliminating this step right here, and then just jumping from the derivative of 4x squared gives you 8x, like that's fine, you can do that. I just wanted to show that intermediate step since we don't have a lot of practice with power rule. Okay, let's take a look at number 2. Now, our one problematic term here with number 2 is that term, 1 over x. That is not written in a polynomial form right now, okay? But I can rewrite this function to put it in a polynomial form. That's going to be negative 4x to the 5th plus 2x cubed minus 1 over x. I can rewrite that as x to the negative 1 power plus 6. And then once I have the polynomial written in this form, once I have the function written in this form, I can use power rule to differentiate, okay? So f prime of x, I can pull negative 4 out front. The derivative of x to the 5th is 5 times x raised to the 4th power plus the derivative of 2x cubed, I can pull 2 out front, and the derivative of x cubed is 3x squared minus the derivative of x to the negative 1 power. If I use power rule, that's going to be negative 1 times x, and then we're going to subtract 1 from the exponent, so that exponent becomes negative 2. And the derivative of the constant term 6 is 0. Okay, and I just want to go through and simplify this now. So that's going to make f prime of x equal negative 4 times 5, that's negative 20, x to the 4th, plus 2 times 3, that's 6, x squared. Negative 1 is going to change that term to positive. Negative makes that term positive. And then we can rewrite x to the negative 2. Like if you want to leave it in that form, that's fine. Or if you want to write the last term as 1 over x squared, that's okay as well. All right, either one of those is fine for that last term. Okay, let's take a look at 3 and 4. So 3 and 4 look somewhat similar, but we're going to have to take the derivatives of these a little bit different. Okay, so when we look at number 3, we have the function f of x equal to 3 over 5x squared. Now that function is not a polynomial, nor is it written in a polynomial form right now. Okay, so I want to rewrite this function, putting it into a polynomial form. So I can do that. I can rewrite this as 3/5, and then 1 over x squared is the same thing as x to the negative 2 power. And then once I have the function written in this form, I can now use power rule to differentiate. So that's going to make f prime. I'm going to pull 3/5 out front, and then take the derivative of x to the negative 2 power, which is negative 2x to the negative 3rd power, which is going to make f prime of x equal to negative 6 over 5 times x to the negative 3rd power. Or if you want to rewrite that back as a rational function, you can make this become negative 6 over 5 x cubed. Okay, 4 looks similar, but what's different in number 4 is we're taking that whole denominator, 5x, and squaring it. Which means we're going to have to do like one additional step here. Okay, so what I'm going to do for this one is I'm going to apply the exponent to each of the factors in the denominator. So that becomes 3 over 5 squared, which is 25, times x squared. And then I can work this out very similarly to how we did number 3 now. So I can rewrite f of x as 3 over 25 times x to the negative 2 power and then I can differentiate. You can take the derivative, so I pull 3 over 25 out front. The derivative of x to the negative 2 is negative 2 x to the negative third power. So that's going to make f prime of x equal to negative 6 over 25 x to the negative third power. Or if you want to rewrite that back in the form of a rational function, that's going to be negative 6 over 25 x cubed. All right, let's move on to the next example. So the next example asks us to find dp dt. Again, we mentioned last time that that was one of the notations that we could use for a derivative. That would be the derivative of p with respect to t. Okay, so dp dt, is the same thing as saying like find p prime of t. Okay, so what I want to do first is I want to rewrite the function p where we can use power rule to differentiate it. Okay, so when I look at rad t, that's a rad function. It's not a polynomial, but I can write it in a polynomial form. So rad t is like t to the 1/2 power plus 3 times the cube root of t squared. That's going to be 3 times the cube root of t squared. I can rewrite that as t to the 2/3 power. And once we have the function written in that form, we can now take its derivative using power rule. Okay, so p prime or dp dt is going to be equal to the derivative of t to the 1/2 power is going to be 1/2 t. And then we're going to subtract 1 from the exponent. So 1/2 minus 1 makes that exponent become negative 1/2. And then if I want to take the derivative of the next quantity, I pull 3 out front. And the derivative of t to the 2/3 power is going to be 2/3 times t. And then we're going to subtract 1 from the exponent. So 2/3 minus 1 is negative 1/3. Okay, which is going to make dp dt equal to 1/2 t to the negative 1/2 plus 3 times 2/3 is going to be 2 times t raised to the negative 1/3 power. If you want to leave things in that form for right now, that's fine. We can also write this back in the form of a radical. So 1/2 t to the negative 1/2 power, that's going to be 1/2 times 1 over rad t, so that becomes 1 over 2 rad t. Plus 2t to the negative 1/3 power is going to be 2 over t to the 1/3 power, or 2 over the cube root of t. So either one of those is acceptable for that derivative for the time being. Okay, we take a look at the next example. Directions here say to find h prime of x. If h of x is equal to x squared minus 2x over rad x. So when we look at this function here, we have the quotient of 2 functions. We don't know how to take the derivative of a quotient yet. We're going to learn that in the next lesson. But I don't have to write h of x as a quotient, because what I can do here is I can simplify h of x to put it into a form where I can use power rule to differentiate it. And the way that I can do that is I can take each term in the numerator and write it over rad x. So the first term is going to be like x squared divided by x to the 1/2 power. So if you divide 2 exponents that share the same base, you subtract the power. So 2 minus 1/2 is x to the 3/2 power minus 2x divided by rad x is like 2 times x to the first divided by x to the 1/2. That's going to be x to the 1 minus 1/2 power, which is x to the 1/2 power. And once I have things written in that form, that's in a polynomial form, I can use power rule to differentiate. So h prime of x is going to be 3/2. X to the, we're going to subtract 1 from the exponent. excuse me. So that's 3 halves x to the 1/2 power minus, I can pull 2 out front, and then the derivative of x to the 1/2 is going to be 1/2 x to the negative 1/2 power. So that's going to make h prime of x be equal to 3 over 2 x to the 1/2 minus 2 times 1/2 is 1 x to the negative 1/2 power. If you want to leave things in that form, it's fine. If you want to rewrite this derivative here as 3 rad x over 2 minus x to the negative 1/2 power is 1 over rad x. If you want to write things in that form, that's acceptable as well. And technically with this, like if you want, you can combine that into a single fraction. So your common denominator would be 2 rad x. And you guys are going to need to know this for later on in this chapter, like when we simplify derivatives. So if your common denominator is 2 rad x, I have to multiply the top and bottom of the first fraction by rad x to get that denominator. And then I have to multiply the top and bottom of the second fraction by 2 to get that denominator. Okay, so the numerator is going to become 3 rad x times rad x, which is 3x, minus, and then 1 times 2 on top gives us 2. So this would be like the most simplified form of that derivative. But, I mean, for right now, when you guys are learning this, like you can write it in this form, that's fine. If you want to write it in that form, that's fine. Or to simplify, it's okay. But starting in the next section, we're probably going to start simplifying our derivatives, just to make you guys aware. Okay, on to our next example. So directions here say to find the equation of the line tangent to y is equal to x rad x at x is equal to 1. All right, so we have a tangent line problem like we looked at in the last lesson. Now we know we need 2 things for the tangent line equation. We need the slope of the tangent line, which is the derivative, and we also need the point of tangency. So let's do the point of tangency first, since that's the easiest thing for us to find. So if I plug 1 into my function, 1 times rad 1 is going to make the y coordinate of our point of tangency 1. Okay, now we need to find the slope of the tangent line, and to do that, we need to find the derivative. But the problem is we don't know how to take the derivative of the product of 2 functions. Again, we're going to talk about that in our next lesson. But if I use some algebra here, I can rewrite this function to put it into a form where we can use power rule to take its derivative. And when I multiply 2 exponents that share the same base, so that's x to the first power times x to the 1/2 power, when I multiply 2 exponents that share the same base, we add their power. So I can rewrite this function as x raised to the 3/2 power. Okay, so when I write that function as x to the 3/2 power, I can now take its derivative. So y prime of x here is going to be 3/2 x to the 1/2 power, which I can rewrite that as 3/2 x to the 1/2 power is rad x. And then we want to find the slope of the tangent line. We want to evaluate that derivative y prime at 1, which is going to be 3/2 times rad 1, and rad 1 is 1, so 3/2 times 1 is 3/2. So that's my slope. My point of tangency is the point 1, 1, and I can plug that into my point slope formula. It's y minus the y coordinate 1 equal to the slope 3/2 times x minus the x coordinate 1. So that's your tangent line equation. Let me ask you this question. What is the slope of the normal line at that point? See if you remember that from the last lesson. So we know the normal line is perpendicular to the tangent line at the point of tangency. So if our tangent line has a slope of 3/2, the normal line at that point slope would be the negative reciprocal. So that would be negative 2/3. So again, that's just a reminder from the previous lesson. Okay, so we did one of these examples in the last lesson as well. So directions here ask us to find the points on the curve. F of x equal to x to the fourth power minus 6x squared plus 4, where the tangent line is horizontal. If our tangent line is horizontal, that means our slope has to be equal to 0. So we're going to set the derivative of our function. And because our function f is a polynomial, like I can take its derivative the way that it's written right now. So that's 4x cubed minus 12x. The derivative of 4 is 0. And then we want to find where the tangent line is horizontal, so we're going to find where that derivative is equal to 0. And this just turns into like an algebra 2 or a pre-calc problem. Okay, so we're just solving this polynomial equation here. So I can factor a 4x out, which leaves me with x squared minus 3. And then I can factor x squared minus 3 as the difference of squares. So that's going to factor to x plus rad 3 times x minus rad 3. And that product is going to be equal to 0 when x is equal to 0, when x is equal to negative rad 3, or when x is equal to rad 3. And then we just want to find the y-coordinates of all three of those points. So I'm just going to plug those x values into the original function. So when I plug 0 in, that gives me an output of 4. When I plug negative rad 3 in, that's negative rad 3 to the fourth minus 6 times negative rad 3 squared plus 4. So negative rad 3 to the fourth is going to wind up becoming positive 18. Minus 6 times rad 3 squared. So rad 3 squared is going to... Sorry, hold on one second, guys. I'm sorry, that's a mistake. So negative rad 3 to the fourth is going to be actually 9. Okay, so that's negative rad 3 times negative rad 3, which gives us 3. And then when we square that, that's going to wind up becoming 9. So that's 9 minus 6 times negative rad 3 squared is 18 plus 4, which is 13 minus 18. So that's going to make the y-coordinate there negative 5. And then when I do positive rad 3 to the fourth, we're actually going to wind up getting the same value for positive rad 3 to the fourth. So that's going to be 9 minus 18 plus 4. So our last point is going to be negative rad 3, or sorry, positive rad 3, negative 5. Okay, so those are your 3 points where the tangent line is horizontal. And if you think about that curve, like the 3 points where the tangent line is horizontal is going to give you the local maximums and local minimums on that curve. Okay, so we'll talk more about that when we get into chapter 5. Okay, so we've got 2 tougher problems to close out. Okay, so find the equations of the lines tangent to the parabola y is equal to x squared plus x that pass through the point 2, negative 3. Not sure if you guys remember this, but we actually did a problem similar to this in 4.1 as well. Okay, and what makes this problem more difficult is that this point right here, 2, negative 3, that does not lie on that curve. How do I know that? Well, if that point does lie on your curve, then you should be able to plug the x and y coordinates into your equation, and it gives you a true statement. Okay, which is not the case here. If I plug 2 in the place of x, that does not give me negative 3 as an output. So we have to work through the longer process that we did in the previous lesson, okay? And what makes this problematic is like we don't know what the point of tangency is, or points of tangency are for our tangent line equation. Now, the good news for us with this example is we can determine the slope of the tangent line a lot faster. Okay, so I can get the slope of the tangent line by taking the derivative of our function, which the derivative of x squared plus x is 2x plus 1. Okay, now because the point does not lie on our graph here, we know that our tangent line has to touch our curve at some point, and every single point on our curve is going to be of the form x comma y, but y is the function x squared plus x. So we know our tangent line has to touch our curve at some point, and we know our tangent line also has to pass through the point 2, -3. Again, if you guys like forgot this example, you should go back and watch the very end of 4.1, because I worked that problem out in a lot more detail. I don't want to spend that much time working on this one because I've already shown you one like this in the previous lesson. So if you've forgotten that, go back and rewatch that video. You're going to need to know this for your test. I'm for sure going to ask you one of these on your test. But go back and rewatch that video. It'll give you like the explanation for this in more detail. Okay, so again, we know our tangent line has to pass through both of those points. So I'm going to calculate the slope of the line that passes through those 2 points, okay, which is going to be y sub 2, which is x squared plus x, minus y sub 1, which is -3. So minus -3 is the same thing as saying plus 3, over x sub 2, which is x, minus x sub 1, which is 2, okay? That is the slope of our tangent line. What else is the slope of our tangent line? Well, the derivative is also the slope of our tangent line. So if both of those equations represent the slope of the tangent line, or both of those expressions represent the slope of the tangent line, those two expressions have to be equal to one another. Okay, so we're going to set f prime equal to the slope of the line that passes through these 2 points right here. Okay, so we're going to solve this equation here for x, and that's going to give me the x coordinates of the point of tangency. All right, so I'm going to multiply both sides by x minus 2. We get x squared plus x plus 3 equal to 2x plus 1 times x minus 2, which is x squared plus x plus 3 equal to 2x squared minus 3x minus 2. And then I'm going to move all the terms to the right-hand side. So that's going to become x squared minus 4x minus 5 is equal to 0. And that's factorable. That factors to x minus 5 times x plus 1. So our points of tangency are x is equal to 5 and x is equal to -1. Okay, so again, the two things that we need for the equation of the tangent line is the slope of the tangent line and the point of tangency. Okay, so the slope of the tangent line we get by evaluating our derivative at these points. So when I take y prime of 5, when I plug 5 into the derivative, we get 2 times 5, which is 10, plus 1, which is 11. So that's the slope of the tangent line. And then I will also want the point of tangency. So the x coordinate is 5. I plug 5 into the original function to get the y coordinate. So 5 squared is 25 plus 5 makes the y coordinate 30. And once we have slope and point, I can plug that into my point slope formula. Y minus 30 is equal to the slope 11 times x minus 5. So that's the first tangent line equation. The second one I get by plugging 1 into the, or sorry, negative 1 into the derivative. So y prime of negative 1 would be 2 times negative 1, which is negative 2, plus 1, which is negative 1. So that's the slope of the tangent line. And then I also need the point of tangency. So the x-coordinate of the point of tangency is negative 1. When I plug negative 1 into the original function, we get negative 1 squared, which is 1, plus negative 1. That makes the y-coordinate 0. And then once we have the slope and point, we plug into our point-slope formula. So that's y minus the y-coordinate 0 equal to the slope, negative 1, times x minus negative 1, which becomes x plus 1. And that right there is our second tangent line equation. So again, you have to work through this longer process when the point that you're given is not a point on the graph of your function. Okay, that's not your point of tangency. In this particular case, we had to do all of this extra work to find the coordinates of our point of tangency. Okay, last example for the day. Directions ask, what is the value of k plus c if f is differentiable everywhere? Okay, so this pertains to like what we discussed in the last lesson, but I didn't want to work through this example in the last lesson because it would have taken too long to take derivatives of our functions. So I'm going to look at it in this example where we can take these derivatives much more easily. Okay, now, being differentiable everywhere implies two things. Okay, if our function is differentiable, it also has to be continuous. Okay, so when we look at this function, where are we worried about the function being continuous? Well, we're worried about the function being continuous at x is equal to 3 because that's where the function changes. Okay, so to be continuous at 3, that means the limit as x approaches 3 from the left has to be equal to the limit as x approaches 3 from the right for our function. Okay, so for our left-hand limit, we're going to use the top function, 2k x squared minus x. And then for the limit as x approaches 3 from the right, we're going to use the bottom function, x cubed plus cx. Okay, now to take both of these limits, I can use direct substitution. So when I plug 3 in the place of x, we get 3 squared, which is 9, times 2k, that's 18k, minus 3, is equal to, when I use direct substitution on the right-hand side, 3 cubed is 27, plus 3 times c. So if I move the variable terms to the left-hand side and the constant terms to the right-hand side, we get 18k minus 3c is equal to 30. And I'm actually going to simplify this really quick because all of these terms here are divisible by 3. So I'm going to divide both sides of the equation by 3. So that gives me 6k minus c is equal to 10. So that should tell you if we're solving for k and c, like this problem is going to break down into solving a system of equations. Okay, so that's going to give us the first equation in the system. Okay, to get the second equation in the system, for our function to be differentiable everywhere, again, the one spot that we're worried our function being differentiable at is where the function changes. Okay, so to be differentiable at a point, that means that the slope on the left-hand side and the slope on the right-hand side have to be the same at that point. If those two slopes are different, then your graph is going to have a corner or a cusp, and your function is not going to be differentiable at that point. Okay, so we want the slope as we approach 3 from the left-hand side to be equal to the slope as we approach 3 from the right-hand side. Okay, so for the slope on the left-hand side, we're going to take the limit as x approaches 3 from the left. To get the slope on the left-hand side at 3, we're going to take the derivative of our function. So the derivative of 2kx squared is going to wind up becoming 4kx minus the derivative of x is 1. And that's going to be equal to the limit as x approaches 3 from the right of the slope of the function on the right-hand side. So I want to take the derivative of the bottom function. So the derivative of x cubed is 3x squared plus the derivative of cx. Again, c is like a constant, so I can pull c out front. The derivative of x is 1, so c times 1 is going to be c. And if I want to get the slope on each side, I can go ahead and use direct substitution for these limits as well. So when I plug 3 in the place of x, that gives me 12k minus 1 equal to, when I plug 3 in the place of x, we get 3 times 9, which is 27, plus c. And then again, I'm going to move the variable terms to one side and the constant terms to the other. So we get 12k minus c is equal to 28. And that's the second equation in our system. So if we want to solve the system, so our first equation here is going to be 6k minus c is equal to 10. Our second equation is 12k minus c is equal to 28. I'm going to multiply the bottom equation by -1 so I can eliminate the variable c. Okay, so that gives me 6k minus c is equal to 10, and then -12k plus c is equal to -28. So when I add those two equations, we get -6k equal to -18, which makes k equal 3. And once we have that k value, I can plug into either of these two equations to solve for c. So I'm going to go ahead and plug into the equation on the left. So we get 6 times 3, which is 18, minus c is equal to 10, which makes -c equal to -8, and c equal to 8. But we're not done because the problem asks us to find k plus c. Okay, so k plus c is going to be equal to 11 in this case. Okay, so really good problem here. It plays on something that we've talked about already. It plays on the idea of continuity that we talked about in chapter 3. It just adds a new layer onto this problem because to be differentiable, not only does the function need to be continuous, so the limit as x approaches 3 from the left and the right have to be the same, but it also has to be differentiable, which means the limit as x approaches 3 of the slope on the left and the limit as x approaches 3 of the slope on the right have to be equal to one another as well. Okay, so that's it. That wraps up this video. We'll see you guys in class later. Take care.